Hi, I'm Dr. J, and this is a video about t-test. As usual, down below there's a PDF version of these slides, and up top there'll be a link to the playlist all about statistical inference from a Bayesian and non-Bayesian perspectives. In this video, we're going to be talking about t-test. This is the second video in talking about hypothesis testing. The previous video was on binomial models. Here we're going to be talking about normal models. As a reminder, a statistical hypothesis test has two hypotheses, a null and an alternative, and really these hypotheses make statements about parameters in models. Ultimately, your goal is to make a claim about these hypotheses and either reject or fail to reject the null hypothesis. And I'll remind you at the end of the video about what that really means. All right, so in a t-test, we have data that are assumed to be normally distributed. They're independent, they have some mean mu and a variance sigma squared, and the hypotheses are about that mean mu. So one standard hypothesis is that the mean is equal to a particular value mu naught, the alternative being that it's not equal to that value. And then we have two one-sided hypotheses where an example here is that the mean is less than or equal to a particular value mu naught, the alternative being that it's greater, or you can switch those around so that the null is that the mean is greater than mu naught or equal to it, and the alternative is that it's less than. As before, sometimes it's convenient to have this sort of partitioning of that mean parameter value, but sometimes it's helpful to be thinking about the null hypothesis as just being equal to. Okay, so we'll go back and forth between those two. Here, in order to conduct a t-test, we're going to calculate a t-statistic. The t-statistic is just the sample average minus the hypothesized null value mu naught divided by the sample standard deviation over the square root of the sample size. That t-distribution, if the null hypothesis is true, and we're thinking about the data as being random, so y bar and s are both random, that will have a t-distribution with n minus 1 degrees of freedom. Now we're going to determine the as or more extreme regions just like we did on the previous video with the binomial probability of success. If we have an alternative that states that the mean is less than a particular value, then we'll be looking for t-statistics that are less than or equal to our observed value of little t. If our alternative says that it's greater than a particular value mu naught, then we'll be looking for t-statistics that are greater than or equal to the observed t-statistic that we have. If our alternative says that it's just not equal to it, then again we're going to go and look at how far away it is from the mean of this t, the random t, but since this random t has been standardized, the mean is just 0, and so the formula here is a little bit more simple than the formula we had for our binomial model. Here it's just the as or more extreme region is the absolute value of our random t is greater than or equal to the absolute value of our observed t. Now, throughout all of these statements, that capital T is a t-distribution with n minus 1 degrees of freedom because that's what's true under the null hypothesis. To visualize, before we get to visualizing, let's look at some example data. So here is a situation where we have a normal model and we have a hypothesized value for a mean that says that it's equal to 3. And now suppose we've collected some data and we observed out of the 6 samples we have, a sample mean of 6.3 and a sample standard deviation of 4.1. We can calculate the t-statistic, rounded to 2 significant digits, it's 1.97. Because there were 6 data points, then our degrees of freedom is 1 minus that, or that minus 1, which is 5. When the null hypothesis is true, that's the distribution for our t-statistic. Now we can look at those as or more extreme regions. So the one on the far left is the less than, and since t was positive, that's quite a big area. The right one is the greater than area, and the middle one is the not equal to area. And as before, you'll notice that the area on the right and on the left are equal in that middle facet. And in fact, one of those areas is equal to the area in the greater than plot. So in order to find the p-value for the not equal to, we can actually double the p-value for the greater than. Now, we're not actually going to do this one by hand like we did with the binomial before, but instead we're just going to go right into using R to do the calculations for us. In order to do the calculations R, we actually need to have the data, but here's what it would look like. In this case, for our alternative, that the mean is less than 3, we just have the t-test. We plug in the vector of data observations y. We determine what our mu naught was. In this example, it was 3. And we specify our alternative hypothesis, which in this first example was less than. And we calculate the p-value. In this case, as we saw the picture before, it's quite large. In this case, about 0.95. If we calculate the opposite of this one, right, so the alternative is greater than 3, we calculate the p-value, and it'll be 1 minus the previous one, so 0.05 or so forth. Then we calculate the two-sided version, and we find that it's double what we had for the greater than, about 0.10. All right, so great. So we've now determined how to calculate the p-value depending on which of these alternatives we're interested in. And now we get into, well, what happens if we reject or fail to reject? So just as a reminder, the null hypothesis is in fact a model. So in our case, it's the normal model with independent observations with a mean that is exactly that value mu naught and a common variance. And so if we reject the null, what we're saying is that the data are incompatible with this model. So what does that mean? Well, that means a few things could be wrong. It means that possibly the data are not independent, possibly they don't have a common variance, possibly they aren't normally distributed, possibly the mean is not equal to the hypothesized value, or you got unlucky. If, on the other hand, you make the decision to fail to reject the null hypothesis, then what can you say there? Well, what you can say is that there are insufficient evidence to say that the data are incompatible with the null model, that is, the one that's listed up top. Right? And this is as strong a statement as you can make because there are a variety of reasons, in particular a small sample size, why you might fail to reject the null hypothesis. So that doesn't mean it's true. Okay. All right, let's give an example. So here is an example of a I-beam manufacturing facility. And these I-beams are constructed with a design specification for their thickness, perhaps in the middle, to be 12 millimeters. During the manufacturing process, there's a random number generator that every once in a while decides to take a I-beam for measurement. And so that gets pulled off the assembly line and gets measured in terms of its thickness. And when you repeat this process for 12 example I-beams, you find that you get these particular data. And now the question is, do these I-beams have that design specified mean of 12 millimeters? All right, so you can use the t-test to say, all right, is that mean at 12? And here, in this case, you find a p-value that's what, 0.03 or 0.04. And if you have your standard significance level of 0.05, you might say that we reject the null hypothesis. So at this point, it would be incumbent upon you to go and evaluate why that might have been rejected, right? Are they independent with the random sample? They seem pretty reasonable. Are they normally distributed? Is something else going on there? Do they have a constant variance? These kind of things before you conclude that really it's just the mean that's out of whack. All right, as a summary, so all that we say here, if we reject the null, is that the data are incompatible with this model, but it's not 100% clear yet why. All right. In summary, we introduced this idea of a t-test. We used a p-value in order to determine whether to reject the null or fail to reject the null. Really what we're saying is whether or not the data seem incompatible with the model, or whether there's sufficient evidence to say that. And then finally, even if we do reject, there's more work that needs to be done to verify why that rejection occurred. Moving forward, we'll be talking more about these frequentist ways of looking at things. We'll be talking about, for instance, the correspondence between confidence intervals and p-values. Hope to catch you there.